versus square root NB. And semi-classically speaking, I showed you earlier, square root NB is K, so we can get the dispersion. Okay, so that's how we get dispersion. Okay, so here's a DI/dV spectrum, and here's what happens when you turn on a field. You get a bunch of peaks, and now let's look at magnetic field dependence, because what we want to see is there a non-dispersing peak? Is there a peak whose energy doesn't change with magnetic field? By the way, the difference between this figure on the left and right is that this is just another derivative of this, that's all. And the reason we show this is it's actually easier to see these peaks sometimes when you take another derivative. Okay, so here's the Dirac point. You don't know that this is the Dirac point, but remember I suggested that it might be because it's a minimum in the density of states. And you notice that right at this point, you get a peak whose height grows with magnetic field, but its position doesn't change. This is energy, okay? And in addition to this peak, you get a bunch of other peaks. Here are all the other peaks. Now the interesting thing, next thing to do is to actually index them. And this is really tricky. How do you index these peaks? Now in our case, it was easy because we could actually identify the Dirac point. Typically, if you don't know where the Dirac point is, it's very difficult to index the peaks. Okay, so here's 0. Now I should have called this 1, 2, 3, 4, and so on. I should have done that. But if I do that and try to plot E versus square root NB, I get nowhere. Okay? Remember, all the peaks have to collapse on the same curve as a function of square root NB. Okay, no matter what the magnetic field is. So after playing around a lot, this is the indexing scheme that worked for us. 0, skip this peak, 1, 2, a bunch of missing peaks, 6, 7, 8, and then it goes on continuously. Okay? So then if you plot E versus square root NB, this is what we get for the dispersion. All right? So there's a peak at the Dirac point that doesn't change with magnetic field. There's a bunch of peaks, and if you try to connect a straight line from the Dirac point to all of these peaks, if you could try to connect a line, you'll notice that the only way you can connect all these points together is with a straight line. Okay, there's no other way. There's too much constraint in the system. So close to the Dirac point, you have linear dispersion. Now above a certain energy, there's a jump, right? And as it turns out, this is the energy of the Van Hove singularity, or the Lifshitz transition. So what's happening is the following. So this is the Dirac point that corresponds to this. When these two electron-like Fermi surfaces merge together, you get a doubling of the area. And that's what you see. That's the jump you see here. Okay? Any questions about this before I move on?
Sorry. Why are the peaks missing?
That's right. They're not really missing. They're actually all lumped together. Because of you see what happens to the dispersion. It's slowing down. And because of that, it's the area that matters. And you can think about the area. There are peaks very close to area together in energy whose areas are quite different from each other. So you can either think of them being lumped together, or, if you ask Yang Fu, he'll say they don't exist. But the area doubles. So that's what we see.
Now a question, in a previous slide you showed that at your suggested Dirac point, the Prof incidentally became a peak.
Yeah.
I didn't understand why.
There's a peak at the Dirac point that you expect to see for Dirac systems, and that's it. It's as simple as that.
So, you would expect that.
You expect a peak at the Dirac point, yeah. Yes?
So look, it should see two areas.
No, just one. Oh, yeah, the other one. So you can ask, where's the Landau level for that other Fermi surface, right? And that's at a different, we don't see those. I can show you why later. Okay? Those areas are completely different. Remember, Landau levels are all about areas, and that area is very tiny. So the energy at which you should see those Landau levels is completely different. Exactly, so eventually you'll see it. Right? not at these entities. Okay. All right, so what I glossed over was the fact that you don't have one non-dispersing peak, but you have three non-dispersing peaks, and the question is, what are these two extra peaks due to? And it took us actually a long time to figure this out, because it seems like the only way in a Dirac system that you can get non-dispersing peaks is if you have either a Dirac cone, right, or you have massive Dirac fermions. That's the only way. But we were really confused because we could see the evidence for a Dirac cone. So the question is, where do the massive Dirac fermions? So it looks like, what it really looks like is we have a massive cone and a massless cone. We have both of these existing in the same system. So the question is, how do you first of all, how do you provide mass to these Dirac systems? And the second is, how can you have a coexistence of the two? Yes, Ilya?
So you're treating the back structure as being fixed, and then you
Yep.
apply a magnetic field and then
Yep.
But have you noticed that there aren't other changes to the back structure?
That's a very good question. That's a very good question. So, the only way we know is by trying to fit the data according to the simplest possible theory. That's it. So our simple theory actually fits, the simple analysis fits the data. So we didn't have to invoke anything else. One example is G factor. If you have a large G factor, everything can change. But we didn't have to include a G factor. All our analysis was done based on a very simple idea, and it all fit the data. Okay?
But so shouldn't there be a spin splitting somewhere like this that related to the G factor?
Say that again. Shouldn't there be?
G factor, there is spin splitting?
Yeah. So the spin splitting is too small in this case. If you say that the G factor is 2 on the scale, so the Landau level has a certain width. It's smaller than the width of the Landau level. Yeah. So we can't see it. Yes. Sorry?
What is the real G factor in the system?
For the surface state electrons, if from our work it seems like it's 2, close to 2. But we don't know the answer. We don't have any experimental measure of that G factor. There are other systems where actually you can see the effect of G factor on the Landau levels. There we can tell you what the G factor is. Here we can't tell you what the G factor is. We know that it's small, and that's about it. Okay, so how do you break the symmetry? So here's the conjecture. Here's our undistorted 100 surface. What if you had a distortion of this kind? So you take one sublattice. Here's the orange sublattice. I know you can't tell the colors very well, but this is the orange sublattice. And you shift it, right, in this direction with respect to the yellow sublattice. So you can see these orange dots have moved this way. The yellow dots have moved this way. Okay? So if you make this distortion, right, then what you notice is that along this direction, these are the two mirror symmetry lines. Along this direction, you still preserve mirror symmetry, reflection symmetry. But along this direction, mirror symmetry is broken. All right? And so if you do have such a distortion, where mirror symmetry is broken along one direction and preserved along the other, then actually you can do a calculation to show that in this direction you still have the two intact Dirac cones, but in this direction you'll get massive Dirac cones with opposite mass. One will have positive mass and one will have negative mass. That's what theory predicts.
What chooses the direction?
Of what?
How do you know, how could you have...
That's a spontaneously broken symmetry. Okay? So you can ask the question, how is this happening? What's the proof that this is happening? I'll give you proof that this is happening because we do STM and we can see the atoms. Why this is happening? From our data, it seems like it's happening close to the surface. It's a surface relaxation. Okay? It's not happening in the bulk, but I'll show you that. Yes?
You see the big walls,
Sorry, do we?
Domain walls of spontaneous symmetry breaking.
The what?
The domain walls.
So not yet. It would be very cool to see that. But let me go ahead and show you the data. Okay. So yeah, sure, that sounds great in theory, and actually you can calculate Landau levels. It fits our data beautifully, but that's not proof. I agree. So here all these lines were calculated by theory, and all these dots are experiment, and you can see that the dots line up beautifully with the theory. Everything works beautifully. But the question is, what's the proof that this thing is actually happening, right? That you actually have this kind of coexistence of massive and massless Dirac fermions. So the proof is, it's STM. We should be able to see all the atoms, and if you can see all the atoms, we should be able to show that one sublattice has moved with respect to the other. So here's what I'm going to show you that data. So here's at low biases, you see only one sublattice, and it looks very pretty and it's square. We found out by increasing the bias voltage that slowly, you can already see by 200 millivolts, it's getting very murky. At 800 millivolts or 600 millivolts, it's a huge mass. And we actually, as it turns out, we see both sublattices at these bias voltages. And we can actually prove that by looking at we can do two things to the higher bias images to show you that the symmetry is broken. One is we can take a Fourier transform and look at the imaginary component of the Fourier transform, the phase. Okay? That gives you evidence of broken C4 symmetry. The second is we can look carefully in real space, and if you look carefully, you will be able to see that one sublattice has moved with respect to the other. So let me show you the Fourier transform first. So here's a low bias image. Here's the Fourier transform. You see 4 peaks corresponding to this lattice. Okay? Sorry, this is rotated with respect to this. Sorry about it. Is it? Yeah, I think. Anyway, this is the Fourier transform of this. The imaginary part of the Fourier transform is pretty close to 0. There's not much information there. Now at this high energy, this is the Fourier transform. First thing you notice is that you get these higher Q peaks. That means that the periodicity that you're imaging here is actually √1/√2 of the periodicity that you see here. That means that you're seeing both sublattices here. Okay? The second thing is, if you look at the imaginary part of the Fourier transform, you see an emergence of 2 peaks along one direction and no peaks along the perpendicular direction. And I can tell you later, you can come and talk to me or read the paper. This is proof of broken C4 symmetry in topography. Okay? So this is one way of showing that rotational symmetry. In fact, rotational symmetry in 2 dimensions is the same as reflection symmetry. So this Fourier transform analysis tells you that reflection symmetry is broken. But you can also look with your eyes. It's hard to see from here. If you could see the data, I would point out to you areas where you can see with your eyes. But there's a better way. We can actually construct an average unit cell of this data set, meaning you just average all the unit cells in this sample. And if you do that, it looks like this. And now you see clearly the zigzag pattern. Here's one unit cell, here's the other unit cell, and you can see very clearly that one has shifted with respect to the other. And in fact, if you look at this cartoon, you can see that this shifting should create this kind of zigzag patterns in your topography. And this is exactly what is causing, yes?
But you're not really seeing, you're not seeing the atom, like the nuclei, the atomic cores directly. You're looking at the
Correct.
density of the block
Correct.
states. So maybe the block states are just strange. And
That's a very good point. So we have about 1 billion tests to confirm whether the intensity variations we're seeing corresponds with actual atomic positions or it's some other. So you can do all kinds of things. So one thing we can do, like I said, when you go to high energies, you see all the atoms. We see distinctly the tin atoms separate from the lead atoms. We know that because we can count them. So you have many different tin alloys, and in each you count the number of these bright spots, and if they correspond, if they increase like they should, the number increases like it should, and the density is correct, then the bright spots we are seeing are tin atoms. Now if you take those bright spots and ask where they live with respect to the lattice that we are actually observing, you can tell that this lattice should correspond to, because those are random. Okay? So that's one check, and we do have other checks as well. Yeah, you're absolutely right though. We could be seeing all kinds of things in STM. Just because it's periodic doesn't mean we're seeing the atoms. Yeah. Okay, so 5 minutes, thank you very much. So, one thing I want to tell you is that this material does have a tendency towards a very similar distortion in the bulk. If you went to the end member, tin selenite, and you looked at the 100 surface, you would see exactly what we see in our topographies. So this kind of distortion is not unfamiliar to this system. Okay, so then that begs the question, okay, so if this distortion is creating the mass, if we change the tin content, can we actually tune this mass? Okay, so that's what we wanted to do next. So here I'll show you a series of data, Landau level spectra taken at different tin concentrations. Okay, and this data set has a huge amount of information. So I know this is the end of the hour, bear with me. I'm going to try to go through this without, losing you. So here's the topological sample I showed you earlier. Here's the zero field spectrum, and here you can see the 7 Tesla spectrum. Here's the Dirac point, and here are the peaks on either side, which represent the mass. Here's a less tin concentration, again Dirac point, 2 peaks on either side, but it does look just already that the 2 mass peaks have shifted in towards the Dirac point. Here's what we know from ARPES as the critical concentration. This is close to the critical concentration. Here the conduction and valence bands are actually very close to touching each other, right? Beyond this concentration, it's going to become trivial. You still see surface states. You lose this beautiful V shape, okay? It's because the bands are very close, so you don't see the Dirac states that clearly anymore. But you can see that even at this concentration, there's a teeny tiny little Dirac peak. You don't see the mass peaks anymore. Here's a trivial concentration. Surprise, there are surface states here, okay? But no peak at the Dirac point. This tells you immediately that these are trivial surface states. So the Dirac cone is supposed to bridge the conduction and the valence bands. The moment the material turns trivial, there's no such reason. You don't need to bridge the conduction and valence bands. You don't need a Dirac point. You have surface states, but no Dirac point. So if you take our data and we plot it like I plotted it earlier, you see that it evolves in this fashion. And really our picture is that as you get closer and closer to the critical composition, the 2 cones get closer and closer together. They merge, and then on the trivial side, you get this interesting looking surface state. Okay, so what did we learn from this data? Give me 2 more minutes. Can I have 2 more? Yeah. So what we learned is that first we can see the instant when the material goes from topological to trivial just by the missing Dirac point. Okay? The second is the mass decreases to 0 as we approach the critical concentration. So the question, and this is a plot of this mass, which is actually this gap here, as a function of tin composition, and it goes to 0, okay, at the critical composition. The question is, why is this happening? One idea might be that it's because the distortion magnitude that we observe in STM is actually changing as a function of composition. So we checked that. We checked the distortion as a function of composition, and we were very surprised to find that there's no difference. The distortion remains a constant. Even all the way into the trivial side, the distortion is the same. Okay, so the question is, what is causing this? And after a lot of thought, we realized that it was something really important. By the way, this shows you that this distortion doesn't exist in the bulk. It's a surface phenomenon. Okay, this is an X-ray, and I can tell you this later. In any case, so here's what's going on. The broken symmetry occurs close to the surface. It's some kind of surface relaxation. But as you go from the topological to the critical point, the band gap is closing. The effective penetration depth of the surface state electrons goes as 1